Tēnā koutou, tēnā koutou, tēnā koutou katoa. First, I'd like to start by acknowledging Tainui, who own the land that we're standing here today in. I'd like to start my talk by showing you this video clip. And with this video clip, I want to tell you about why I find it interesting and exciting. So, when you're a physical oceanographer, you study waves and currents. And the problem with studying waves and currents is you can't see them with the naked eye. You have to think about them and imagine and visualize them in your head. But basically, as the currents move around sandbanks and shape and form them, we can't see it. So when I was doing my PhD in the 90s, satellites had just come into action. The first satellites went up in the mid-80s. And with those satellites, it was absolutely mind-blowingly changing the way we thought about our own science, because everybody was trying to figure out how we could extract information from satellites to take the parameters that we understood about our science. And if you're a waves person, the particular thing that you get from remote sensing and imagery is the breaking wave patterns. They tell us where the waves are. Now, this video clip that I've been showing you is from Tyrone Beach in the Coromandel Peninsula, and it's from the Waikato Regional Council monitoring station there, and it shows it's been going there for 20 years. And what you can see is sometimes the surf zone is really, really big during storms, and sometimes it's small. You can see really complex patterns evolve, and sometimes you see the beach becomes really simple. They're really, really big rip currents sometimes, and then sometimes really small ones. The beach sometimes has these bumps in it, and sometimes it goes flat. So basically, what these averaged images I've just shown you allow us to do is to take a very complex wave-breaking environment, and when we average it, we see these simple patterns evolve. Now, if we start looking at video imagery and now satellite imagery from around the world, we see these intriguingly regular patterns all around the world. For an example here, these welded bars in Cape Cod, that's a house there for scale, so that's about 1 kilometer. Here, on a very small scale, we see these beach cusps. On Hotwater Beach, the water's so clear there that we can see these crescentic bars that are about 250 meters long. Here on the Aquitaine coast in France, we see extremely regular rip current patterns. And then if we go up in scale, we can see these flying capes in the Sea of Asmod that are about 50 kilometers along. So to figure out how a complex environment with waves breaking everywhere can make some simple patterns, we need to know a little bit about how waves transfer energy in the surf zone. So if we look at the beach, the waves come in from offshore, and then here they begin to feel the seabed, and they begin to break. And as they break, the wave energy basically depends only on the local water depth there. So if you're standing here, the wave energy only depends on the depth here, and not on how big the waves are offshore. So during storm events, all that happens is the waves start to break further offshore. And down here in the shoreline, the waves are quite a similar size. That's pretty odd. So where does all that energy from breaking go? Well, I like to think of energy as buckets of waves, buckets of energy there. So the size of the bucket is equal to the size of the wave, or the wavelength, or wave period, and the amount of water in the bucket is the energy of the wave, which is measured as its size. So we can put current meters and pressure sensors out on the beach and measure the relationship between energy and size, what we call an energy spectrum. And there's an example here, plotted here. This is size on this axis, with the small buckets down here, and then the larger buckets here, and here's the wave height or energy. If you look at this red line here, pictured here, we can see the small buckets have little bits of energy, and this one has a large amount of energy. But if we go down here, this bucket, the very largest scale, is still empty. As we move towards the shoreline, to this blue line here, we can see all of a sudden, this biggest bucket has filled up and is now full of water or energy. Now this is from Tyrone Beach on the east coast, But if we go to the west coast, the situation is even more dramatic. This incident peak here that we can see, the normal waves that we can see, has completely disappeared, and this big bucket has taken all the energy that is available out of those waves and put it in here. So if you're unconvinced by the graph, this video clip has been prepared by my former graduate student, PhD student, Rafael Juarez, and he digitized the shoreline at Tyrone Beach. Each of these yellow dots is the shoreline, and at Raglan or Naranui Beach, which is Raglan Beach. And you can see the little dots go up and down with every single wave coming in Tyrone Beach, whereas on the West Coast beach, the waterline doesn't change very much. It only changes on a really slow cycle. So what happens gradually through time, this low, big bucket of energy gathers up on the beach and begins to pulse seaward and start to scour out little holes. Those little holes gradually continue to grow and make big rip current channels. And it's those rip current channels that you can see so well from the video imagery when it's averaged. That's an example of Tyrone Beach again that I was showing you at the beginning. Now then we can develop computer algorithms that go and extract the channels and also the sandbars like here and clean them up and gradually track what happens to these rip current channels through time. And here's an example. Each one of these dots is a rip current channel. Obviously, these are the areas where the waves weren't breaking, so we couldn't get information. And this is through the summer of 2000. This is days on this axis, and this is longshore distance on this axis. So in the beginning here, we had 3 big rip currents on one side of the beach in the summer. And then the big winter storms came by and changed the beach, reconfigured it, moved it around. And then at the end of the summer, the beach had rotated, the sand had moved to the other end, and those big rip current channels had gone completely to the other side. Well, repeat the same experiment 2 years later, in 2002, and the same thing didn't happen. The 3 rip current channels went away completely and were turned into 11 or 12 small rip current channels. Well, that sort of gives you the indication that the beach isn't very predictable and we can't make any sense of it at all. But that's not true. We've now analyzed many, many, many years of this data. And we can see that at least some of the patterns are related to rotation. Down here, we've got the alongshore scale and the cross-shore scale plotted here. And you can see that the bigger the alongshore scale, the bigger the cross-shore scale. But over here, we've got the amount that the beach is rotated. And you can see quite easily here that when the beach is in a strongly rotated state, we get those really big scale currents appear. Well, what has this got to do with everyday New Zealanders? Well, I have to say, I admit, I am not solving cancer. I'm not coming up with the cure to cancer here. But having said that, New Zealanders have put an immense amount of money into property. In fact, the amount of money that we have in coastal property is up in the billions of dollars in New Zealand. And much of those assets are below the 5-meter line, all right? And a lot of those places, and many of our beaches, are having severe erosion problems through time, and the erosion problems appear to be getting worse. If we look at this schematic from the Waikato Regional Council website, we can see on this axis all the Coromandel beaches plotted, and these lines represent the distribution of houses in the coastal zone in the Coromandel. And this is 0 to 50 meters, 100 meters. And so within this 50-meter line, there are an awful lot of properties that are close to the ocean. Well, when we superimpose that on my shoreline database from Tyrone, which is in the middle here somewhere, we can see, and I haven't picked a particularly dramatic shoreline change. This is a pretty typical rotation for Tyrone. We could see at the end of the beaches, the shore can move up to 40 meters. So if you're one of the properties at the end of the beach, you're way too close to the shore. Interestingly, we tend to profile beaches and monitor beaches right in the middle, which is exactly the worst spot to monitor some of these beaches because it's the place that changes the least in New Zealand, and on our Coromandel beaches at least. Well, that was the slow onset hazard associated with coastal erosion, and it kind of creeps up on you as storms compound through time. But we also, with rotation, comes those really big-scale rip currents. And those rip currents, they're a much more immediate hazard. In fact, they can even be life-threatening. Now, you can't study the speed of currents from a video camera, or at least not easily. And so in order to do that, we have to deploy things like these drifters. These are neutrally buoyant PVC plumbing pipes that have been filled with insulation foam, and so they float just beneath the surface. And sticking up out of them is another PVC pipe, and on top of it is a GPS. And so that GPS can track these drifters through the surf zone. Of course, health and safety first. We had to get the Coast Guard's help to pick these up because they tend to get swept out to sea. So that's our Coast Guard, also our technician, Dean Sandwell, who happens to also volunteer for the Coast Guard. Very handy. Okay, so this is our experiment at Naranui Beach, which is Raglan Beach. At the south end of Naranui Beach is a very big rip current system which tends to persist through time in the same place. Now, interestingly enough, just very, very minor changes in the wave patterns can make a very big change to the rip currents. These dots here are where we deployed our drifters, and on the first day, every single one of them, except for this guy here, got shot out to the open ocean and we had to go and pick them up. On the second day, the wave height changed by only 10 to 15 centimeters, so a tiny little bit of a difference. And that activated the braking on this outer bar here. See that? And that braking forced all our drifters to come back into shore, right? So only one escaped. So the escape strategy that you might have, or the hazard that this rip current poses, is completely different depending on these little braking patterns. Well, if we scale back, if we zoom out with that camera, we can see our little rip current there, or big rip current down there. But this is what else that video camera shows. It shows the whole delta system offshore of the Raglan Harbor entrance. And that delta system is the one that boats often overturn on. It's quite hazardous. If we plot georectifier images or get a bird's eye view of our images, we can then plot our braking wave pattern on the Waikato Regional Council multi-beam data, which we collected for them a number of years ago. And you can see that those braking patterns really line up nicely with where the sandbars are, which is very encouraging. Interesting, this little area here, down here, is very important for surfers. The surfers love this wing of the ebb tidal delta. Our PhD student, Sean Harrison, digitized the location of this ebb tidal delta through time, and these are the results of his efforts. And you can see these blue lines are where the ebb tidal delta is in late, that's December, January, and February. These red lines are where it is in November, October, September. And so you can see that it moves in and out or flaps its wings like a bird. Very interesting. Along the side here, as it flaps its wings, the surfing conditions can change completely along that side. So you have seasonal changes in the surfing conditions. Well, I never really thought about surf that much. And in fact, surf has become much more important in my life than I ever expected. New Zealand's one of the only places in the world where we protect surf breaks. And that their surf breaks, I think 17 of them, are listed as nationally significant breaks in the New Zealand Coastal Policy Statement. Wow, we really are passionate about that to the point where we can protect them. Now, what are we protecting about a surf break? What we're protecting here is what's called the peel angle, which is the speed at which the whitewater moves down the crest and how long it takes for that whitewater to move down the crest, or the length of the ride. Interestingly, those are exactly the parameters that I can extract from my video imagery and have been doing for years. So we have this program called the Surf Breaks Research Program, and we have sites around New Zealand that we've elected to study in more detail. We've got Aramoana and Whareakiaki, and that's down in Dunedin. And what's interesting about those sites is that the surfing conditions are completely regulated by the Port of Otago dredge spoil dumping program, which is offshore of here. We have Lyle Bay here, where the airport, that's in Wellington, where the airport extension is supposed to influence this, or should influence the way the surf changes along that side. Down here we have Whangamata, and we have, in New Zealand, one of the most controversial issues between the Whangamata surfers and the marina development within the harbor, so that's why we have that site. Right? And finally, we've got our natural sites, Manu Bay, which is a rocky shore break, close, one of the most famous. Piha, up to the north, which is one of our earliest surfing sites in New Zealand, and finally, Wainui in Gisborne. Now, one of the challenges with monitoring surf is that we're trying to detect a human-induced change in a system that is varying hugely, not only between seasons, but also between years and even long-term changes with changes to the wave climate. And in fact, if we look more closely in New Zealand, our waves are really strongly driven by climate cycles. This shows the summer wave conditions and whether or not they're correlated with the Southern Oscillation Index. So down here in New Zealand, our significant wave height, our wave period, and the direction of our waves, well, significant wave height increases with La Niñas. If we go over here to the States, in the west coast of the States and Canada, it does the complete opposite. You get big waves during El Niños. And so the whole Pacific is changing with one side getting high, the other side getting low, and so on. Fascinating. And because it was a big study, we needed all those people on the paper. In fact, my PhD student, Victor Godot, who's just finished, worked with the NIWA wave hindcast that was developed by Richard Gorman at NIWA to look at the wave climate in much more detail. And he found that not only the Southern Oscillation Index was important, and waves coming from the Pacific Ocean, but all sorts of other wave climates around the oceans. We have one of the most complex wave climates in the world. Here we have the Southern Oscillation Index, and yes, it's correlated with La Niñas on the north coast, but it's also correlated with El Niños on the south coast. The Southern Ocean, of course, is a huge driver of wave conditions in New Zealand. The Southern Annular Mode and the zonal wave number 3, funny name, I agree. And of course, the conditions in the Tasman are important. And finally, even the Indian Ocean is important. Because we're situated at a higher latitude than Australia, the waves from the Indian Ocean can come round from underneath Australia and hit our southern coast. So this indicator, which is the dipole mode index, which is the movement up and down of the Indian Ocean, also affects the wave climate around New Zealand. Now, with a 45-year wave hindcast, that should be enough to see changes. We should be able to detect if our wave climate is changing. It's problematic, I admit, because these climate drivers have very long-scale changes, and so it's difficult to detect a mean change over something that's varying on such a long scale. Also, over 45 years, the way we force our models, the wind conditions, they are also changing. The way we measure them is changing. But with our best guess, our most knowledgeable, actually it's not a guess, with our best calculations, we think that they are changing. This is the mean wave climate around New Zealand, and it's changing by about 2 to 6 centimeters per decade. But for a coastal hazard kind of issue, it's not the mean conditions that are important, it's the extremes. And we can see that the size of extreme waves is changing by a few centimeters per year. It's not so much the size, it's the number of events. So all these points down here show that the number of events per decade is also increasing. Now, what's the problem? We really, really lack validation data. New Zealand has only 3 buoys that are functioning all the time around our coast. If we look at somewhere like the British Isles, they have about 24 or 25 boys working all the time to validate their hindcasts. So the last thing I'd like to say is that new data is coming online all the time, and that new data is the satellite data that we have. And one of the things that's fascinated me is the effort that people who run satellite programs are going to make it accessible to everyday people. So now you don't need to be a supercomputer program or be able to remove all the clouds yourself. You could do it yourself. And so I just wanted to finish with this image, and I'm going to try and get the actual image. And so this shows, and it's animated, and you can go to the site. This shows the red dots here show all the satellites that are active in the world right at this moment, right now. And all those satellites stream to various commercial operators, but also government operators, and a lot of them are making that data freely available to us as academics. So, hang on, let's go transfer back. So that's all I have to say. Thank you very much. Thank you. I'm glad to see so many people here. I appreciate you coming. And of course, I do need to make some acknowledgments. I'd first like to acknowledge my family. Of course, the students. You make this the best job in the world. You know who you are. The technical masters who put all the data together, even in the office, the computer people, all those people. I'd like to acknowledge mentors. And in the beginning, it was scientific mentors helping me with the research. But gradually through time, those people became mentors on how to communicate, how to project manage, how to navigate the New Zealand science system, which can be very tricky sometimes. On Vision Mātauranga and learning more about that. And also, I'm really fortunate to have academics in my family to help me along. There's a bunch of people that I would call opportunity makers who sometimes don't realize they're helping you, but somewhere along the line, they open a door that changed your pathway. And of course, you took the chance when it was there, but they made that key thing that made your life different. Of course, the many colleagues that I've worked with, the publications that we worked on together, and there'll be colleagues in the future that I'm looking forward to working with on new problems. But finally, I'd like to acknowledge the University of Waikato. And, you know, I came from Canada, and I came down to this place in the Southern Ocean, a long way away from the real world as I conceived of it at the time, but still, I have had the ability, and I've had the opportunity to create a mark on the world, which is absolutely amazing to me. And I want to acknowledge Chad and Bruce and Richard Price before that have made these opportunities for us. And I want to finish with one last thing, and that's the number 274th. We're ranked 274th. If you think of all those universities in South Africa, in Canada, in the States, in England, in the Netherlands, in Germany, that is pretty amazing for a small place down in the South Pacific. That's all.